The video subsystem contains a few video IP cores, and when a processor needs to change the setting for one of these video IP cores, it usually sends all this data through the FPRO bridge and then the FPRO bus, and then it goes in here. Of course, the processor sees the whole subsystem as a bunch of registers, but we know that it has a few cores inside it, so we would need some sort of a mechanism to actually access each one of the cores separately. So similar to what we did with the MMIO subsystems, we had an MMIO controller. In here, we will have a video controller that allows the processor to interact with the different video IP cores separately. So let's take a look at the specification for this video controller. So the video controller, which is this little piece in here, allows the processor to interact with each one of these IP cores. And each one of these IP cores will have a small memory, basically, a bunch of local registers, similar to what we saw in the IO cores. However, one thing that is super important to understand in here is in the IP cores, the processor goes to one of the IPs, sends certain data, and that's it. It leaves it at that point. And it might interact with the outside world or the outside physical world with a bunch of, for example, LEDs or switches. So in a video subsystem, it's a little bit different in that actually we have a video, basically pixel stream that goes all the way through to the VGA, but there's no actual interaction with the outside world outside of that video stream or pixel stream. The processor itself does not access that at all, actually. It does not interact with the pixel stream. It doesn't change the pixel stream itself. It's something that is going on continuously so that the VGA or monitor actually can display a meaningful picture reliably. So what the processor does, it actually just interacts with the video IP cores by changing some of its local memory or registers. So why would an I/O controller actually or a video IP core actually has local memory? Well, some of them is to change basically whether you want to bypass it or not. But more importantly, it might have like really larger memory because some of them, for example, the mouse sprite in here will contain the shape of the mouse pointer that you want. So you need to actually store it. Other cores will have, like, for example, if you're dealing with or developing a video game, that means you need a character. So you need to store the character, and we'll see this later in a different video. But the bottom line is actually the controller or the CPU here or the processor interacts with the different IP cores by basically writing into these particular registers in here, not the pixels, just the registers internally here. One more thing is a video controller is similar to the MMI controller. It actually decodes and multiplex addresses. However, it really does not multiplex addresses. We do not need to multiplex any addresses. So a video core does not have any external signals in here. So there's no reason for the processor to read from it. So there's no reason for me to get the video IP core, this one actually, to send any data to the processor. It's only one way, and it's generally speaking, it's the processor changing certain settings or changing certain information within the local memory or local registers. So this video controller, as we'll see shortly, it only decodes. There's no need for multiplexing. So let's dig deeper into that video controller. So in order for us to actually build that video controller, we need to specify a couple of things. So the video cores, I will divide them into a couple of types. We will have a few normal video cores and a single frame buffer core. So these ones here are highlighted in blue and red. So let me talk a little bit about the red one and at least what's its purpose. So the frame buffer core, which is something we're going to see later, it's just basically a blank canvas. It's a really large memory that contains information about a whole frame, like basically all the pixels within one frame basically stored. And the reason why is because you can actually get the CPU to go to that frame and write to this specific location for a specific pixel, and it put a certain color. For example, let me assume that this is the frame buffer. You can tell the processor can tell that frame buffer, hey, go to this particular pixel and put basically the color purple in it, and you can basically do this pixel by pixel. So that's what the frame buffer does. And a frame buffer actually is a large memory. So if we take a look at the number of words we needed to store, it's about 1 million words, and a word is actually 32 bits. Okay, yeah, about 32 bits. That's what we will be actually. We'll go to the details about it, but for now, all we need to know is that that frame buffer actually allows us to write about 1 million words in it. Normal video cores are a little bit different. They have smaller memory, and I'll have a bunch of them, not only one. So a normal video core, for example, the video subsystem is not as versatile as an MMIO controller. I don't have so many protocols that I need. So for our purposes, we're just going to stick to 8 cores. Okay, and so we're going to have 1, 2, 3, 4, all the way to 8. and we're going to develop some of them, and we're going to put like some dummy cores in the others. But the bottom line, we're going to just basically develop that system with 8 normal cores. So if we need 8 normal cores, that means I need 3 bits to address these cores. Each one of these 8 cores will have about 16,000 words. You might think about it, and you might think like, why would I need 16,000? I mean, for the MMIO core here, we have 32, not 32,000, just 32 registers. In here, I have 16,000. And the reason why is because you might be storing certain patterns or certain shapes. For example, if you're developing like a game and you have a bunch of characters, you might have like 10 characters or so. So you need to actually store the pixel information for all these characters. So we need a little bit larger. So we have less number of cores, but each one of these cores will have much, much larger memory so that you can store more meaningful patterns in it. And if you think about it, a 16K would need about 14 bits. So this information is really useful because we're going to be using it to actually build the video core, because the video core does something very similar to the MMI controller in that it actually just decodes addresses and actually helps me and routes certain signals to the different IP cores. So we have seen an address, like I dissected an address when we talked about the MMIO address translation, and we said, okay, so we usually have 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4 is actually 24 bits for the address. And we decided that we're going to take the 8 most significant bits, which is basically the most significant byte. We're going to put it to C0, and that will tell me that that's basically that the processor needs to, or trying to communicate with the bridge, or basically with our system. So that's already taken, and we ignored the least significant 2 bits because we're dealing with word addressable. So we don't, and our memory is aligned, so we're not just going to touch on those. And then in the MMIO controllers, as a reminder, we took the most significant bit here, which is that particular bit, and we said, okay, if you set it to 0, that means you want to communicate with the MMIO. And we said at that point that if you set it to 1, that means you need to communicate with the video core, and that's what we're going to be doing now. And then, of course, the orange ones were basically, we used some of them, basically 5 bits in here to address the 32 registers that we have, and a few bits in here, basically exactly 6 bits in here, actually to address which slot number out of the 64 slots that we can, and that's how we did it. And the rest, we said that we set them to X's in here because we will need them for the video subsystems, and now we're about to use them. So in terms of address translation using the video controller will do address translation a little bit separately, whether it's dealing with the normal video core or one of the frame buffers. So if you're dealing with a normal video core, as a reminder, we have 8 of them, and each one of them will need 16K. So we take a look at this here. The first, basically, the C0 is the same because you're trying to deal with a bridge. And then we have the video controller here. We set it to 1, this particular green bit, and then we ignore these. And now we're left with the orange, but there's a little bit of a change in here as well. We're going to take that little bit in here. You can count the number. I forgot which number it is. I believe this is number 20 or something. We're going to see it in the code shortly. But if you set this to 0, that tells me that you're dealing with a normal core. If you set that to 1, that tells me that you're dealing with a frame buffer. We're going to see the frame buffer shortly. Okay. Now, we know that this is a normal core. We know that we need about 3 bits to actually address which core we want. So we're going to actually use these, and we need about 14 bits to actually figure out which one of the 16,000 rows that we need, and that's what we're using in here. So this particular example, I'm basically trying to access core number 5, and I'm trying to access the register number 13,643. And that's how we're going to do it. So the video controller will actually help me decode this particular address this way. It's a little bit different than MMIO. I would urge you to actually just pause a little bit and just compare the two, so you make sure you understand the differences. We still have a bunch of X's in here, and we said that we need them for the video controller. And as it turns out, yes, we do need them specifically for the frame buffer. That's why we kept that particular, that we use that many bits in here is specifically for the frame buffer. And in the frame buffer, we don't have a bunch of them. We just have one. So we don't need to address, we don't need to figure out which one we're addressing. It's just a single one. So again, we have the bridge in here in blue. We ignore the least 2 significant bits because we're dealing with word addresses. Basically, each one of these rows or each thing that we're addressing is actually 32-bit, but they're arranged in bytes and they're basically aligned at 00. And then we have here that we're dealing with a video I/O core, and just a quick reminder, this is usually decoded by the bridge. It just activates some video chip select at the bridge level, as opposed to MMIO chip select. And then here I'm saying, hey, I have a frame buffer core. It's not a normal video core, okay? And then the rest of them here, which is about 20 bits, are exactly to address one of these 1 million words that I need. And that's how a frame buffer, how video controller should work. So let's take a look at the code for this particular controller. And again, as a quick reminder, that particular code should actually just follow this frame buffer core addressing in the normal video core. So let's take a look at that code and see what's it composed of. So the code specifically, this is the video controller. It takes a few inputs from the bus. So for example, it tells me the video chip select. This is basically that little one green one in here. Usually the bridge up there in the system just activates this, a video write, basically just a write signal. And then we have a video address, which is 20 bits, which are basically these ones in here. Okay, all the 20 bits, regardless of whether you're dealing with the normal video core or actually the frame buffer. And then we have the data, which is 32 bits, because this is how it's actually word addressable, not byte addressable. And then we have like a couple of interfaces as outputs. These are all outputs, whether you're dealing with a frame buffer. Okay, so if you're dealing with a frame buffer, which is this one in here, you'll see that you have a frame chip select. Basically, it's based on this little purple guy in here, and the frame write, basically it's just the write signal will be translated that way. And then we have the 20 bits, which are the orange one in here, the frame address, and then the data itself, which is 32-bit. And it's basically just mapped from here directly. However, if we're dealing with a video core, a normal video core, if you actually take a look at it, it's actually, we're going to have basically a slot chip select array. Because we have 8 of them, this only one of these bits would be activated to figure out which one. And usually we use these 3 bits here to activate it. These 3 bits will be connected to a decoder, and the output of this decoder will be connected in here. Basically, this is the output of a decoder to activate one of the slots, basically one of the 8 cores that we have. And internally, basically, that's basically the write address. We'll see what it's basically to distribute the write signal to all of them, or actually using the decoder, we'll be just basically using some decoding. And in here, basically these are, if you think about it, they are 14 bits, which are these here, the address that internally we need, and we also distribute it to all of the cores. And in here also we distribute it to all of the cores. It's actually the data. And if you take a look at the code very briefly, it's actually really, that's exactly what it's doing. It's actually, for example, for the slot address, for example, it's taking the number of bits from 14 to 16, which is that one in here. Okay, and I'm just renaming it. And then for the register address, I'm just taking this particular 13 bits, I'm renaming it. So now I have them separately in here. For the frame, if I'm doing the frame select, it has to be, this has to be 1, and this has to be, if you're dealing with a frame buffer, both of them should be 1. That's what I'm testing. If you're dealing with the normal slot one, that should be 1, and the other one should be 0, and that's what you see in here. And then I do a few like basically there's only decoding, there's no multiplexing. Again, that particular video core in here, the process will only write to the different video cores. It doesn't read from them, so I don't need a multiplexer. All I need is actually just a decoder. And you can read the rest. It's really straightforward. The frame address, basically, I'm just taking the video address, like the 20 bits and so forth. It's just basically normal mapping, and that's about it. And we have some genvar in here to distribute the write signals and the read signals and so forth. This is how we're doing the decoding to activate one of the slot addresses if you're dealing with a normal video core, which is basically taking that particular number and activating it and putting 1 on it.